Okay, we're going to prove that 3 to the power n is always odd. So let our proposition p to the n equal 3 to the power n. N is a positive integer, and we're looking at our initial step, which we can call p of 1 sometimes, and we just simply substitute the 1 in for n, and that'll be 3 to the power 1 or 3, and that's clearly odd. So it's true for the base case for p of 1. So we assume true for some p of k, where k is also an integer, and that means that that implies that we have 3 to the k. Now this is a little bit different here. We couple things different here, okay? So what we're not doing is a left-hand right-hand sort of thing, what we do with sums. We're saying that we're assuming it's true that it's odd, okay? So that's what the proof centers around. So we need to use a definition of odd number. So 2 times integer plus 1. So a is some integer. Did you also notice back here in the previous line too that we didn't do a left-hand side, right-hand side routine with that? We just said it's clearly odd. 3 is clearly odd. Nothing odd about that. Oh, hold on. So goofy dad jokes aside, it's the definition of an odd integer. So we would be required to also prove, if it's true for p of k, that it's true for some p of k plus 1. So when n equals k plus 1, in other words. So sharpening my pen here, a little bit finer font there because we've got a little bit of algebra to do. In fact, we have index laws to do. And so if it's also true for p of k plus 1, this implies that we have 3 to the k plus 1. Now, index laws, as I said, if we have a to the x plus y, where a is some base, x and y are indices, a to a power which is made up of x plus y, you should know by now that that's a to the x multiplied by a to the y. Index law number 1, they sometimes call that one, and we can do that here. So this would be 3 to the k times 3 to the 1. Or we could say that it's 3 times 3 to the k. We can swap the order around because it's multiply, and 3 to the 1 is merely 3. We need to incorporate this identity up here. Okay, a bit like, in a sense, like what we did with the sums, the series, but not in exactly the same way. But basically we need to incorporate 2a plus 1. Now 3 to the k is the same as 2a plus 1, that's assumed. So we use that assumption like we do in a number of our inductive proofs. And so we can go 3 times, instead of 3 to the k, the 2a plus 1 from above. So again, just using that from there, because we don't have to prove that's true, that's assumed true in the proof. And that can be written as 6a plus 3, and 6a plus 3 can be written as 6a plus 2 plus 1. Remember, we're trying to prove that this is odd. So we have 2 outside of 3a plus 1, plus the 1 stays outside, which is a strategy we've done with some of our direct proofs. So it's an inductive proof that's using some elements of the direct proof. Now 3a plus 1, let that, sorry, wait on, I've got to do one more thing first. We've got to show that this here is an integer. 3a plus 1 is an integer. So 3a plus 1, that's a 3. 3a plus 1 is an integer. And 3a plus 1, we'll let it equal b. So here we will have 2b plus 1, which is consistent with the definition of an odd integer, which is odd. So the proposition P of n is proven using mathematical induction since it's true for P of 1, and when P of k is true, it's always true for P of k plus 1. So that's proven. So 3 to the n is odd. Awesome.